Everybody remembers the problem of endogeneity, that is when x and e are correlated. If you have a regression model y is equal to a plus b x plus e, then you know that OLS estimators or the general linear regression model is not appropriate when x and e are correlated. Do you remember that very clearly? Okay. So today we will only talk about how that problem can be solved. Okay? So think of a situation where and assume what is the implication of this? What happens if this happens? This is the implication. Okay, so if x and e are correlated, we know that the implications are, if you use the formula, beta hat is summation xi minus x bar y minus y bar upon summation xi minus x bar, that is neither consistent nor unbiased. Right? And why is it neither consistent nor unbiased?
Because the sample size increases, then the value of
because the formula beta hat is equal to summation xi minus x bar y minus y bar upon summation xi minus x bar is derived from the idea that beta is equal to covariance xy upon the variance of x. And to derive that formula, you have to assume that x and e are uncorrelated. If x and e are not uncorrelated, then beta is equal to covariance xy upon the variance of x is not a formula for beta. So if you replace covariance xi by summation xi minus x bar y minus y bar upon n and the variance of x by summation xi minus x bar square upon n, you get an estimator of beta only if covariance x and e is equal to 0. With the covariant pattern which is consistent and unbiased and all. If the covariance x and e is not equal to 0, then you obviously don't get that, because that's why the whole line of thinking is wrong. So how does one resolve this issue? And we know that there are a lot of times when covariance XE is not equal to 0. Right? One of them is, of course, you will omitted variable bias. The other case is when there are errors of measurement in the X variable. And the third case is when Y depends on X, but X also depends on Y. So X is not genuinely exogenous, but X is also endogenous. That is, y is dependent upon x, but x also is dependent upon y. If that happens, then x and e get correlated. It's a very big problem. So how does one try to solve this problem? One way of solving this problem is to look for a variable called z, zi, which has the property that covariance xi zi is not equal to 0. Alright? But covariance xi ei is equal to 0. Yeah, so you think of a third variable called z. So that z is correlated with x. but Z is not correlated with T. Okay? Z is correlated with X, but Z is not correlated with T. Such a variable is called an instrumental variable. Sorry, covariance, I'm sorry. Covariance. Yeah? Zi is equal to 0. Then we call Z an instrumental variable. Okay, we can think of Z as an instrumental variable. Okay, right? Now, how do you use this instrumental variable? Right. One way of using this instrumental variable is a famous method called the two-stage least squares. There's a famous method called the two-stage least squares. What is a two-stage least? Or see, really look at it this way. Okay. Now, if you look at it this way, think of covariance Zi, Yi. Okay. Think of. You have to estimate beta. Yeah? What that be equal to? Sure? Yeah? Right? This by definition is 0. Okay? This by definition is 0. So this is equal to beta covariance xi z. Right? And therefore, beta can be obtained as covariance Zi Yi upon covariance xi zi. How will you obtain covariance Zi Yi? Summation yeah, right, which is essentially right, which is another estimator of beta, which is not the ONS estimator for beta. Because the ONS estimator is summation xi minus x bar, y minus y bar upon summation xi minus x bar square. So, we'll give this another name, beta hat, the instrumental variable estimator, ID. Okay? So, beta hat works as an instrumental variable estimator. Right? Beta hat works as an instrumental, beta hat ID is what we call as an instrumental variable estimator. Okay? Now, will it be consistent? Will this estimator be consistent? Think of the law of large numbers. He says yes. Any idea, any argument why it should be consistent? Should it be consistent or should it not be consistent? Yeah, so because by construction covariance Ei Zi is 0, right? So what do you have? Beta is covariance Zi Y upon covariance Xi Zi. In the numerator of the estimator we have summation Zi minus Z bar Y minus Y bar upon N. So it is sample estimate of the covariance. As the sample size tends to infinity, we know that the numerator goes closer and closer to the actual covariance, Zi Yi. We know that the sample size becomes larger, the denominator summation Z minus Z bar Xi minus X bar upon N gets closer and closer to covariance Xi Zi. Because these are sample moments, they get closer and closer to the population moments, that's the law of large numbers. So the sample size becomes larger and larger and larger, the IV estimator will be a consistent estimator. The IV estimator will be a consistent estimator, whereas the OLS estimator will not be a consistent estimator in this case. Right? Okay, now what I'm going to do is, I'll ask some of you. Okay, we'll use the Feynman method. There is a very, very famous physicist called Mr. Richard Feynman. Have you heard his name? Yeah? No? He is of course a great teacher, and I learnt a very interesting idea that he used to use. We used to use some variant of that. Feynman said that you'll understand an idea clearly only if you can imagine yourself explaining it well to an infant or a toddler. We used to use the idea of a grandmother. Right? Okay, so one of you from each side will tell me how you explain this idea to your grandmother, you have now told her some basic statistics and all that. So your grandmother knows the law of large numbers for you. But she forgets, so you have to keep on reminding her. So how will you explain the fact that IV estimators are consistent whereas OLS estimators may not be consistent to your grandmother or to a toddler? Yeah, who will try it first? It doesn't matter if you go wrong. No? So if you can't, then you not understood that. If you can, you have. Okay, let me explain it to all of you. Suppose you are all my grandmothers. Right? Okay? So the problem is, if you have y is equal to alpha plus beta xi plus ei, right? So let's start. So I'll again So we have yeah? Sure? Right? Yeah? So without making any further assumptions, all that I am doing, this is 0. Sure? So, right? What is the OLS formula for beta? Beta hat is equal to Okay? As n becomes very large, where does this part go to? Covariance y-axis. So here. As n becomes very large, where does denominator go to? This. Right. So this quantity is actually beta plus something. So therefore it's not a beta hat, which is not a consistent estimator of beta, but it's a consistent estimator of beta plus covariance xi ei upon variance of xi. And we never know what is covariance xi ei because ei is by definition an unobserved term. So we only know that beta will not be a consistent estimator unless we assume that x and e covariance x and e is 0. Unless we explicitly assume. But it's a very dangerous enterprise to explicitly assume that covariance x and e is 0 because that requires us to say for sure that there is no omitted variable bias in our model. That is, we have not omitted an explanatory variable that is included also in the relation, that is correlated with the included variable. We are saying that our x variables are measured without error. And we are also saying that x is purely exogenous and not endogenous. And further we are saying that all these three conditions hold simultaneously. So we are putting a lot of requirements on our model to argue that beta will be a consistent estimator of beta. So we are not sure. So what we then do is, we say that let me think of another variable x. Okay, let me think of, so can I write this off? So let me think of another variable x, another variable z. So I have them all. I say that I will think of a variable zi such that so I go and search and identify another variable z which is correlated with x but not correlated with the error. Not correlated with the error. Right? Such a variable z is called an instrumental variable or an instrument. Yes. Thank you. Second time I made this. Because of that you remember that property, right? Right? So z and e is not correlated and z and x are correlated, you have to remember that. Right? Okay, if by forgetting it twice makes you remember it more, then that's better.
So but for us to assume that Zi as a variable we are introducing, there has to be in the regression model something that we should have otherwise forgotten to include, which is already correlated to x.
No, not necessarily. I'll tell you how you can solve this. Okay. So think of which is now why? Because alpha is a constant and covariance zi ei we have set to be 0. Right? Okay? So beta becomes now right? beta becomes now covariance yi zi upon covariance xi z. So if you have to develop a formula for estimating beta, what will that be? This implies that beta hat is equal to right, which is different from the beta hat under OLS, because that is summation xi minus x bar y minus y bar upon summation xi minus x bar square. So we call it the instrumental variables estimator, right? We call it the instrumental variables estimator or an ID estimator. Okay. Now let's see how we can practically use this. Okay. How we can practically use this. Can I write this off? Everybody understand? Okay. So that was first challenge. Now tell me each of you how you will explain it to your grandmother. Who will take the challenge now? If none of you takes it, then I think you will not understood. I will explain it again, which will be very boring. Why introduce Z? So let's answer a question. Who will answer a question? Why do we need to introduce Z? Absolutely. See, we want to estimate beta. That's our job. And that estimator of beta has to be consistent. That's the least requirement that you can have. As the sample size becomes large, your estimate should get close to the actual. When you are using an OLS model, you are not sure whether X and E covariance X and E is 0. Unless it's a very well sanitized kind of a model. In the real world data, whoever told you that your X variables are all measured properly and all that way. So it's very likely that covariance X and E might not be 0. In which case the OLS estimator will not give you a consistent estimator of beta. So, but you want to find an estimator of beta. So you want to find a way around that. In order to find a way around that, we find the variable Z. So that Z is correlated with X but not correlated with E. And then develop an alternative estimator, which is essentially covariance ZY upon the covariance of ZX. We find an alternative estimator, which is the covariance of ZY upon the covariance of XZ, which will be a consistent estimator because sample size becomes large, the numerator will go to covariance yi zi, the denominator will go to covariance of xi zi because the law of large numbers, and beta hat IV will tend to beta even if X and E are correlated. Even if X and E are correlated. Okay? So come on, now grandmother please. Who will take the first? See, she asked a question, we got a lot of clarification. So we will summarize this idea in about 3 to 4 sentences. Yeah? which is called consistency.
Yeah, that's consistent. We want a consistent estimate. But if we go to find the consistent estimate of beta, there is a possibility that it actually does the estimate actually doesn't go towards beta. And if we don't want that to happen, then we have to assume that covariance of x and y is zero. But there is a significant chance that that is not zero. If that happens, then we find the variable z I is going to be such that covariance of x and z is not equal to zero. If x and z equal to zero. So if we now with this find beta type, then we will find we will get a consistent estimate. And under that condition, we get the instrumental variable beta.
And the formula for the instrumental variable will differ from the formula for the OLS estimate. So we get a consistent estimate.
So when we have y is equal to alpha plus beta xi plus ei, we say that y